Okay, so that was less than perfect, but I'm learning, just as you guys are learning science. And the reason we're doing revision videos is the same reason why I've practiced this piece for about half an hour now. Okay, it's so that we get better and better at the stuff we know. And as well as which, the things that we learn in science class are like, when I'm doing the violin, how to hold the bow, how to get the right notes. And if you've got any constructive feedback for me, please let me know, because I'd love to get better at playing the violin. But what you're learning is things like the scales in the lessons, so that you know where the notes are, how to play them. But then we get to exam questions, and that's like playing a bit more of a tune. Okay, so we're asking you to take your knowledge, and it might be take your knowledge from lesson 1 and lesson 4 and bring it together to answer one question. And that's why we revise, to bring all of our knowledge together, and then we can pull it apart in different sections to answer the questions. Okay, so at the end of the lesson there will be some practice exam questions for you to do, because you don't get to be any good at an instrument just by playing scales. You have to practice the tunes as well. But the more scales you know, the easier the tunes are. Anyway, let's stop the music analogy and let's move on to what we have to know. You have been it has been put on the system, so you should be able to see the list of objectives, everything you need to know, and we'll be doing this over 3 lessons. So today's lesson won't cover all of the objectives, but it will cover all of the theory of waves objectives, the ones specifically linked to everything you might want to know about sound and vision will be the next 2 lessons. Okay, so let's take a look at what we need to know. So you might remember this bit of paper. I have used it in previous lessons, and I also used it on my little revision song. What I'm expecting you guys to do, by the way, is to make your own revision resource. If you like this poster and want to copy it, by all means, copy the poster. However, what I would say is try and make something on your own. So on my video channel, if you go back a bit, at the end of the sound waves part of the topic, I did a short song about everything we'd learnt so far. Maybe you want to continue that song or make up your own song. Maybe you like mind maps or spider diagrams, whatever you like. You're making a revision resource, and then you're going to try and answer the revision questions. Because it's not just about getting stuff into your head, it's about getting it out as well. So, stuff that you need to do, you need to be able to name the different waves. So we've got transverse waves and longitudinal waves. Okay, those are our 2 different types of waves. Okay, and we need to do an example of each. Longitudinal wave is sound. You don't get many other longitudinal waves with the compressions and rarefications. Transverse waves are pretty much every other types of waves. So let's go in on this a little bit and refocus. Yeah. So we can see we've got peaks and troughs. We've got one wavelength is one peak to the other. And these are the sorts of waves that you see everywhere else. These are the waves on the ocean. These are the electromagnetic spectrum waves. These are the waves that you see. Okay? So these are light waves. So yeah, you need to know examples. For longitudinal, it is sound. Transverse waves are pretty much every other wave, including light. So the next thing you need to be able to do is label the wavelength, which, as I've said, is one peak to another, and also to label the amplitude. Okay, and the amplitude is the energy the wave has. So how much energy does this wave have? It's the displacement of the wave from the resting position. So you can see I've got a straight line there, which is the resting position. And the amplitude is from the resting position to the peak. it should be the same as from the resting position to the trough. We never ever measure peak to trough because we're looking at how far it's displaced, how far it's moved from resting, from nothing. So if you had a wave on here with nothing, you wouldn't be able to see anything. Okay? However, the more displacement it is, the more energy it has. So in the case of light, the brighter it is. Okay? In the case of sound, because we did look at the fact that we draw sound waves like this, it's how loud it is. Okay? A wave that's straight along here would have no energy, it would have no volume, it wouldn't exist. Okay, the other thing you need to know is the units. Okay, so units aren't that difficult. Okay, wavelength. Length gives you the clue, and we always measure length in meters. Okay, and the wave speed as well, which isn't on this poster at the moment. I'm going to pop it on in a second. Just wait with me. Okay, so here we've got wave speed, and it is the speed at which a wave travels. Rather unsurprisingly there, the letter is V for velocity. The speed changes in different media. Okay, so this is just like our speed of sound, which speeds up if you put it through something solid. So the speed of sound in diamond is 35 times faster than the speed of sound in air, which is pretty cool. You may well remember that that's because sound needs particles to bump together. And in a solid, the particles are all close to each other and aligned with each other. So it's really easy for a sound wave to travel through them. Whereas air, you've not got very many particles. And indeed, in a vacuum like space, there's no particles at all. I was watching Star Wars the other night and criticising it for all the pew, 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 pew noises into the space fights. And it's measured in meters per second. And we write that as m/s. If you wanted to write it as ms to the -1, you can do, but that's not expected until A level. Okay? So that's wave speed. It's a speed. Okay, speed. And that's why we measure it in meters per second, because it's a speed. Amplitude as well, I've not really mentioned, is also measured in meters because we are measuring the height. And the final one, frequency, we use the letter F, and it's the number of waves that go past a fixed point in 1 second, and it's measured in hertz. So 1 hertz is 1 wave goes past in 1 second. 2 hertz, 2 waves go past in a second. 100 hertz, 100 waves go past your fixed point in a second. Okay. I'm going to talk about anomalous results and things like that in a minute, not right now. Okay, so next thing I want to look at, how are waves used to communicate? So we look at these dudes. They're not communicating very much, are they? But if you think about what they're actually doing, giant slinky. So longitudinal waves, this is what we use to sound. This is what is happening right now, going into your ear. We'll be looking at the ear in another lesson, so we're not going to do that right now. But they're the ones that look like this. And you can see the wave being sent along. Okay, longitudinal wave, it goes along. Okay, so we've got our compression going down. The compression's the wave, really. The compression is going down, sending those messages with sound. So that's how we use longitudinal waves for communication, because we use sound for communication. The next one, which is the transverse wave, which is our electromagnetic wave. Okay, so this is what we are seeing. And when we've got a nice long wave, okay, so we've got, say, maybe a radio wave, we use that for watching TV and listening to the radio. As the waves get a little bit shorter, we've got maybe a microwave, which is our mobile phones, our Wi-Fi's. Wi-Fi's a radio micro, sort of in the middle. And as the waves get, and as the wavelength gets shorter still, we've got our lights. Okay, so we've got the stuff we can see. You're watching this video, you're using our longer wavelengths and our nice shorter light so that you can see what I'm saying. You can see this as an example, which is fantastic. So that's how we use the waves to communicate. Okay, so we're back to our little diagram again, and the wave equation is the next thing I've pulled out for us to do. Okay, so our wave speed is equal to our wavelength times frequency. And the thing in physics is that the units usually make some sort of sense. So wave speed, meters per second, wave length is in meters, frequency is in hertz, but if you remember, hertz is waves per second. So that's per second, we've got meters per second. Okay, so wave speed is meters per second, okay, because frequency is waves per second. So wave speed is wavelength multiplied by frequency. Okay, next thing, why are waves used to communicate? So why do we use this stuff to communicate? I've told you how we do it. We can listen, we can see, we can use Wi-Fi and TV and all that amazing sort of technology that's really caught on in the last 30 or so years. Okay, just think when I was your age, we had no Wi-Fi. It just didn't exist. That's a really modern use of waves to communicate. Why do we use them? Because our senses are designed to use this stuff. Our senses are designed to use these waves to hear with. And these waves as well, we can, some animals can feel the noises coming through the ground. So if you're stomping through the ground and creating waves in the ground, then they can feel them as well. Our transverse waves, we can see a certain part of the electromagnetic spectrum. Different animals can see different parts of the spectrum. So a bee, for example, can see ultraviolet as a colour. Just as we can see red and orange and blue and violet, they can also see ultraviolet. So the next time you look at a white flower, it might actually be giving off a colour that you can't see, which I think is amazing. But yeah, why do we use them to communicate? We use them because our senses can detect them. Okay, we can detect them, we can turn them into something useful in our brains, and I think that's amazing. So I've already said that longitudinal waves travel in the direction of the wave. Okay, the direction of travel is the same as the direction of the wave. The wave goes along. Okay. Transverse waves are a little bit different though. They are displaced, so they're traveling this way. So the information is going along here, but they're traveling up and down. Okay, so we're seeing them going up and down, but the information those waves are carrying is actually going this way. So remember, trans means opposite. Okay, so a transverse wave is going in the opposite way to where the information is going. Okay, that displacement is not the way the information is going. Okay, that's really sort of an interesting one to get your head around, really. The wave's going up and down, but the information's going across. So if we look at these, we've got some things in common. Okay, we've got wavelengths. They've both got wavelengths. They've both got a direction of travel, and they've both got a speed and a frequency, but Longitudinal waves need particles. Transverse waves don't. Now, I was saying about the speed of waves changing. Longitudinal waves will get faster the more particles you put in there. So they move faster through solid than through liquid, and faster through liquid than through gas. Whereas a transverse wave travels fastest in a vacuum. And it can go, 12 million miles a minute, the fastest speed there is. And that's the speed of light in a vacuum. But we experimented, didn't we, with changing the speed of light, which was really cool. And that's where we get our refraction and dispersing. And again, you're going to do this in another video. But I just wanted to talk about this because, they've got lots of things in common. They're both waves, but the big difference is this one uses particles and this one doesn't. The more particles you have, the more this speeds up. The more particles you have, the more this slows down. So transverse waves slow down when you try and put them through a liquid or a solid. And of course, if that solid is opaque, as in if you can't see through it, it's not transparent, it will stop the light wave. So that's why we get shadows. And I know you've done all about shadows way back in Key Stage 1, and we're not covering them at the moment. But if you've got shadow questions, do ask. Shadows are cool. So the other thing that we need to do now is the wave equation. Sometimes you're asked to rearrange it. I'm going back and forth on this because I've started off with some of the easier ones and I'm moving on to the harder ones now. So we are getting quite hard. You may be asked to rearrange the wave equation. Now we've got it here. And I've also put it in a little triangle here. So if we wanted to calculate lambda, the wavelength, we cover up lambda and we see it is speed divided by frequency. If we want to calculate frequency, it's wave speed divided by wavelength. Okay? Now I know that quite a lot of you were doing really well with this because I've seen all your answers to my previous questions. So really well done on that. But we can always do some more practice, can't we? The last part. Okay, so this is the very last two. Oh, no, sorry, this isn't the last two because we also need to look at anomalies and calculating means, which you were all really good at in my live lesson. But I do want to go over it again because it's revision. We're practicing. We're going over stuff. And then we're going to put it to good use with our exam questions. So, standard form. There are lots of useful videos on the internet about this. But if you've got your calculator, you can play along. So turn on your calculator. And there is this button here, times 10 to the, which puts things into standard form. There is a way of getting your calculator into standard form and mode, but it's going to take me a few minutes to figure it out. I will pause the video and figure it out in a minute and show you how to do it. Okay, so if I was to type 6 times 10 to the 3, okay, so I used my times 10 to the button there. 6 times 10 to the 3 means 6 with 3 zeros after it. So it should be 6,000. Because if I know that a lot of you can do 10 cubed in your head. So it's 10 times 10 times 10, which is 1,000. So we're doing 6 times 1,000, or 6 with 3 zeros after it, which is 6,000. Okay, and that's all standard form is. It's telling you how many zeros are after it. So 5 times 10 to the 7, for example. Okay, oh, sorry, I've put in an extra times. 5 times 10 to the 7 should be 5 with 7 zeros after it. Let's see. Indeed it is. It really is as easy as that. If you've got a minus number, then instead of adding zeros to the right of your number, you add zeros to the left and you use a decimal point. So 2 times 10 to the minus 1, okay, should be 0.2 or 1/5. Okay, so we've moved it one space to the right. We've put a 0 point in front of it. 2 times 10 to the minus 5. We're going to have 5 zeros in front of it, so it's going to be 0.00002. 2 times 10 to the minus 5. It would be if it set it up correctly. So I'm just going to, The easiest thing to do for your calculator, you don't actually have to understand standard form. If you get a standard form question in your test, you get your calculator and you put in the sum. So the wave speed is 12, it wouldn't be 12 because you only have single digits, 1.2 times 10 to the 5, which is the same as 12 times 10 to the 4 because it's the amount of zeros that are coming after it. And then you might have a wavelength of, 2 times 10 to the minus 8. Okay, so we've got our wave speed and our wavelength. We're finding our frequency, 6 times 10 to the 12. So you would just write that down as your frequency. Do you have to actually understand what the numbers mean? No. It's nice if you do, but if you don't understand it, you can just pop it in your calculator and get an answer. That makes me happy.